Welcome to yet another class with Dr. P. Today we are going to see how we can be able to determine the half-life equation for the first order reaction. Remember that in our previous class we had discussed how we can be able to derive and also obtain the first order rate equation or rate law for a reaction. Now we are going to do a follow-up in that class by looking at how we can also determine the half-life of a first order rate equation. Now we had said before that the half-life of any particular reactant is simply the time taken for that particular reactant concentration, with emphasis on the concentration and not on the mass, the reactant concentration, to go to half its original concentration. And for a first order reaction, how do we determine its half-life? We are going to determine the half-life looking at the first order rate law or equation. Now in our previous class we had derived the first order rate equation as concentration of A is equals to AO, okay, to the exponent of minus KT. That was what we derived at our previous class as what? As the first order rate equation for that reaction. Now looking at the half-life, but let me put the topic so that we don't forget. We are looking at the half-life. We are looking at the half-life for what? The half-life equation for half-life for a first order reaction. Half-life for a first order reaction, and I have started by saying that we have A is equals to AO to the exponent of minus KT. That this equation is the first order rate law or rate equation for the first order reactions. Now from here the half-life can be simply calculated or determined. Half-life equation. So if we take A to be the initial concentration of the reactant A divided by 2, and we take our time T to be the half-life, we can do what? Substitute this equation. If this is equation 1, this is equation 2, this is equation 3, we can simply do what? Substitute. Okay, we can simply substitute. Okay, we can simply substitute equation 2 and 3 to equation what? To equation 1. So it means that we'll now place where we have A with this and T with this. So here will now become what? Will now become to imply that we have A O all over 2 representing this is equals to AO, and then the exponent of minus K, instead of T we write T half. That is what we are going to have, and this is our equation 4. Now at this point in time it is important for us to know that this equation here can be rewritten. Okay, this is the same thing as saying 1 over 2 times AO. So equation 4 can be rewritten. Okay, so we can possibly link it to our calculation. So to do that, we can say our equation 4 can be written as what? 1 over 2 dot AO is equals to what? AO to the exponent of minus KT half. Okay, that's our equation 5. And with this, it is simple. We know that, of course, this will cross this. So we can have a half is equals to the exponent of minus KT half. This is equation 6. Okay, and now with this, we'll be forced to remove this exponential sign. And when we remove this sign from here, we introduce a natural logarithm. to this particular left hand side. So it means we'll now have the ln of what? It implies to have the ln of what? A half is equal to minus k half. This is equation 7. Now, with this, it is easier for us to know that this is the same thing as saying the ln of 0.5 is equal to minus k t half. We can possibly look for what? Look for the half-life by simply saying that the half-life is equals to what? The ln of 0.5 over what? K. And the ln of 0.5 is what? Is what? 0.693. Am I right? Okay, so this is the same thing as saying 0.693 all over k. And this, of course, is the equation that defines the half-life of a first order reaction. So simple and so short. Do not forget to like, do not forget to follow my Facebook page. Don't forget also to subscribe my YouTube channel. Don't forget also to comment and to share. Until next time, I remain your Dr. B. It is bye for now.